Welcome back, Cubs. In this video, it's the last of the chapter on water. Uh, so, as you can see behind me, we've got some water up at the cabin for this lecture. Water, incredibly important, most abundant liquid on the Earth, covers about 75% of the Earth's surface. 70 to 90% of all life is composed of water. So where we find that water is interstitially, so between the tissues. It's also the medium for tens of thousands of biochemical reactions. So it's incredibly important for life. For life as we understand and know it, water is one of those essentials for being the medium for those reactions. Now, it's possible that life can exist in other mediums. That's something that we're still exploring. So it consists of two hydrogen and one oxygen atoms. The bonds are polar covalent. Recall from the lecture on intermolecular forces, that strong polarity that exists between water molecules. So the molecular geometry is bent. And big piece of water. So anytime you come across a question regarding water, you're not sure of the answer, guess hydrogen bonding. That's how important it is to the molecule of water. So two different water molecules are going to be attracted to each other. Specifically, the negative dipole region found on the oxygen of one water molecule is going to be attracted to the positive dipole region of hydrogen on a separate water molecule. So while it's not an actual bond, this strong intermolecular force, specifically dipole-dipole, allows water to have some of its special characteristics. So it should be a gas at room temperature, but it's not. It's a liquid. Why? Because of the strong attractive forces of hydrogen bonding between water molecules. It also gives rise to the shape of ice or solid water. So solid water has a hexagonal shape. So it looks like a hexagon if you line up those water molecules. You get a hexagon there. So solid ice is going to be less dense than the liquid. Why? Because of that hexagonal structure. There's going to be less water molecules per unit area as a solid versus a liquid. Because it's less dense, ice floats. And it's a good thing that ice floats because otherwise we would never have our lakes unfreeze in the summer because it'd be ice all the way down. So solid ice is less dense because of that hexagonal shape. That hexagonal shape is due to the hydrogen bonding that occurs. So here we have a drawing of hydrogen bonding in water. We can see the negative dipole region be attracted to the positive dipole region of another water molecule. We only have four here. If this was a solid grouping of ice, then we would have these six molecules in that hexagonal structure. So some calculations using energy changes with water. The molar enthalpy fusion of ice is just over 6 kilojoules per mole. So that means if you want to melt 1 mole of water from a solid to a liquid, it requires about 6 kilojoules. Then the other is this molar enthalpy of vaporization. This is how much energy is required to go from a liquid to a gas for 1 mole of water, 40.79, pretty high. So this is why steam burns can actually occur. So when the water goes from a gas to a liquid, that amount of energy gets released. If that steam condenses back to water on your hand, those 40.79 kilojoules get exposed to your hand, then causing the burn. So it's going from a gas to a liquid, energy is released. Say that again. From a gas to a liquid, energy would be released because the particles aren't moving around as much. So they don't contain as much energy that gets released to the environment. That's why a steam burn can happen on your hand. And then sample problem A found in your book. You pretty just multiply the 40.79 kilojoules times the number of moles of water present. I'll post another video walking through sample problem A. So that's the end of Chapter 10 lecture. If you have any questions, please reach out via discussion board or remind or email. Have a great day, Cubs.